Well, thanks everyone for coming. Thanks for having me here yet again. We back to the fact. So yeah, I'm going to be talking about this thing that I work on called catalytic space. In particular, I'm going to be talking about a paper that came out earlier this past year about randomization and time-bounded catalytic space. First, yeah, let's define the model. So, in a typical space-bounded setup, we have three tapes. So we have an input tape of n bits, which already has the input written in it, and it's a read-only tape. Can't use it for memory, of course. Then we have an output tape, which for decision problems we think of as just having one bit, and it's write only. We can also think about, for example, search problems where it's a much larger thing, but regardless, we're going to think of it as a write-only tape. So again, you can't use it to like read or a reader. And then finally, you have your work tape, which in our case, we're going to be mostly thinking about the log space. So this will be like a log n length work tape. And the whole point of this model is to work on what we can solve with only a limited amount of space. And for today, we're going to be talking about the catalytic space model, which has one additional tape. And this is going to be, again, a read-write, okay, work tape, which we call the catalytic tape. And we're going to think of this as being, say, polynomial in length, i.e. much, much larger than the amount of free workspace than what ordinarily provided, which would normally just mean that we can capture some large class like P space or whatever. But of course, there's a catch, which is that the catalytic tape itself is also filled in with some string that is out of our control and has nothing to do with the function, or may have nothing to do with the function that we're computing. And so while you can use this as a read-write work tape, the catalytic condition is that at the end of the computation, this tape has to be in exactly the state that it started in. Hence why it's called catalytic, because like in catalyst in chemistry, it's something that could potentially aid you in your computation or reaction, but at the end is left exactly preserved. So that's the catalytic condition, and this model, without the catalytic tape, of course, we call it log space. So with it, we're going to call it catalytic log space. So CL. And the motivating question is, does this do anything? Is this catalytic tape good for anything whatsoever? So what's obvious is that this catalytic log space class is somewhere between ordinary log space and key space. This is obvious because catalytic log space just has a log space machine within it that it can use. And a P space machine can obviously just run on the all zeros catalytic tape. Can pretend that it's running on the all zeros catalytic tape, since this machine has to work regardless of what's in the initial catalytic. And this model was introduced by Buhrman, I believe, Kutzke, R.M. Loft, and Florian Fielman. The journal version is 2014, and the first one is 2012. There's no journal version. The conference version is 2014, and the first version is 2012, I want to say.
No, I think it was just 14, and we finished writing the paper.
Oh, that was it? Oh, okay, well, there you go.
I have a question.
Yeah.
So usually in these Turing machines, we can sometimes extend the alphabet, like the working alphabet, stuff like that.
I'm guessing here you cannot do that because you could just extend the alphabet so that you kind of write over the catalytic space without writing, without erasing information there.
Well, it depends. If you extend the alphabet, it's all well and good. You just have to accept the catalytic condition on the wider alphabet, right? So if I say when I'm working over, 1, 2, 3, 4, 5, then I just have to know that my catalytic tape, I'm gonna have 1 through 5 and everywhere.
Okay, I see.
So yes, you can't artificially extend it after the fact, unless you, of course, you just like group up pairs of elements and just think of it as this extended alphabet. But as long as you're willing to accept the catalytic condition in any model that you take, then of course you can do whatever you want. Okay, so this model was introduced by the CBPL paper, and they also showed tighter bounds on CL from both sides. So what did they show? They showed first that this thing is contained, and I'll be more specific in a second, but it's contained in both BPP and NP. Right, so given access to either randomness or non-determinism, you can solve this in polynomial time, which is a huge step down from P space, as far as we can tell. And that's maybe the less surprising direction, because again, it seems like this catalytic tape is very far from giving you access to the power of P space. Perhaps not so surprising. What is surprising is that it is also more powerful than either randomness or non-determinism in the space boundary case. So this is pretty shocking, I think, because again, you have no absolute control over this catalytic tape, whether it gives you good randomness, good non-determinism, whatever, like this is completely out of your hands. So it seems, I think that most people were pretty surprised by this. This is the first paper that I listed undergraduate, this had just come out. And so I was pretty surprised by it. And so I said, eventually I'll work on this problem, and it took like, I don't know, 6 years before I remembered that it existed. Here we are. So yeah, this is what this Buhrman et al. Paper showed, and this is, roughly speaking, the actual class inclusions here are the best that we know. And I will just say what these actually are. We have that class TC1 of log depth threshold circuits is contained in catalytic logspace. And this is a class that is more powerful than BPL or NL. In fact, it can compute problems like the determinants that we don't think are in either of these. So it's a pretty strong class. On the upper bound side, we have that catalytic log space is contained in a class CBP. And for today, it is actually worth saying what CBP is, because we're going to be talking a lot about randomness. So, has everyone seen CBP? Okay, I'll just say it one more time, just to be clear. So CBP is a randomized polynomial time algorithm. So it's a polynomial time algorithm which gets access to randomness. But ordinarily, for example, in BPP, the randomness can affect whether or not you get the correct answer. So we say probably 2/3 you get the right answer, and probably 1/3 you can fail, get the wrong answer. In ZPP, you still have this 2/3 probability, at least 2/3 probability of getting the right answer. But instead of getting the wrong answer the rest of the time, you can actually just detect that you're doing the wrong thing and say, I don't know what the answer is. So you'll never actually output the wrong thing. You'll only output the correct thing or fail to output it all. This is, you can think of this as essentially BPP where you can detect when you're making the wrong choice. And it's pretty clear that this is in BPP. It's also in NP because you can kind of guess random strings. Like ordinarily, this is not something that you're allowed to do, but considering you can just say, I don't know. You'll never say the wrong thing, you'll only say, I don't know. Your NP doesn't, your non-determinism doesn't like screw you up and give you the wrong answer. Roughly speaking. In particular, this is an NP intercept code. Okay, so that's the basic setup of catalytic space. And once it's introduced, there were a number of open problems and kind of structural results that came out. So the big open problem that is left by this is how does catalytic log space relate to polynomial time? We have the CBP upper bound, and we strongly believe that CBP equals P. We also strongly believe that we're nowhere close to proving this. So this is the question is it any easier to show CL is in P than to show this? And separately, you can ask the question, what other catalytic classes are there of interest? So for example, introduce randomness CL. And this was by Zaba, Gupta, Jain, Sharma, and Tiwari. And this is just catalytic space where I give you also access to randomness, and we'll define them a little more formally in a bit. You have non-determinism. Syntax correct, let's say non-deterministic. And this is by a lot of the same people as the first paper. In fact, all of them except for Richard Heath. Again, just give catalytic space access to non-determinism. There's non-uniform, branching programs. Originally by detection in 2017. There is, let's see here, right, error prone, you could call it. Catalytic space. This is where we don't require perfect resetting of a catalytic tape, and we ask what additional power we ran. This was same ones as up here. Good name, Tiwari. That's here. And so on and so forth. So there's essentially a whole structural theory that we can develop around this catalytic space, and we can ask basic questions like, can we get similar inclusions, like a ZPP inclusion, which I should say that the answer is basically yes, everywhere you'd expected. Randomized and non-deterministic don't gain any additional power beyond ZPP, as far as we can tell. You could also ask questions from traditional space-bounded complexity. You know, do we have a Savage's theorem for a non-deterministic catalytic space? The answer is no. We've got nothing close. We've got no idea how non-deterministic and deterministic catalytic space relate to each other. You could ask, does NL equal co-NL in the catalytic world? Answer there is yes. You can ask, is there a derandomization with a 3/2 overhead? And of course, that's going to be the subject of today. Prior, it was known that you could totally derandomize it if you assumed you had a pseudorandom generator, which it's not obvious, but it's pretty close to it. But they use it in a pretty cool way, so I don't want to take credit away. And anyway, there's a lot of things that we can talk about here, and I find pretty much every area of catalytic computing to be quite interesting. But for today, we're going to be talking about two things. We're going to be talking about CL versus P, or we're going to be talking about randomized catalytic. Those are going to be the results that we're going to be focusing on today. And I'll just actually state the two main results before we move any further. First is that we can totally derandomize catalytic space. So randomness is not an additional resource to a catalytic machine.
This is a big open problem in the non-catalytic world. Right?
Yes, it should be noted that P space equals randomized P space. So on one hand, we have it, and in the log space world, we don't. We have a 3/2 exponent minus a little bit.
So randomized log space is in space log n to the 3/2.
Minus the low, yeah, you save some like log factor in the denominator, but yeah. So you can think of this as being, halfway between those two results or a stepping stone. But it should also be noted that like, PPCL, this class is between BPL and BPP. And we have no idea how to derandomize BPP. We're nowhere close. So it's also an intermediate class there, but for where we have we have no idea on one end and some idea on the other, and in the middle we get it perfectly. I should also note that kind of to compare it to the randomized space world, the blow up in our catalytic tape is going to be some larger polynomial than than just a 3/2 exponent overhead. So right, like what's going to happen is that the log space is really only going to grow by a constant factor, and the catalytic space will grow by a polynomial factor, which obviously keeps it in the realm of catalytic log space, but it doesn't get as tight of an overhead in the catalytic space as something like like Nissan or Sachs-Joe would. Of course, those techniques don't directly apply to the catalytic world, so just caveating this as you things you might be. The second result is that polynomial time catalytic log space, where I impose polytime run bound, is equal to the intersection of its two restrictions, catalytic log space, polynomial time.
Nice.
So this one's a bit subtle, and I should say a couple words about it. Okay. We do not know if catalytic log space is in polynomial time. We do not know whether it will always run in polynomial time for any starting catalytic tape. Furthermore, even if I told you that catalytic log space is in polynomial time, and that containment holds, it would not hold that catalytic log space is equal to polytime bounded catalytic log space, right? Just because there is a CL, that every problem in CL can be solved in P, doesn't mean that every CL algorithm runs in polynomial time. You may need to actually use all of your free space, this space as free space in order to get the polytime savings. And this tells you that that's not the case, that insofar as CL is in P, CL is equal to its poly runtime bounded version. So yes. This leads to there's an interesting thing that happens if you put these two results together that is also worth mentioning. This is like kind of the synthesis result. It's that
I mean, you'd think that now you can just prove that CL equals polytime CL. Why? Because
CL equals polytime CL if CL is in P.
no way. I mean, why would I think that this should follow somehow? Prove the same thing where P instead of P you have CPP. Then you'd have shown that polytime randomized CL
Equals CL.
CL intersect CPP, which is just
CL. Excellent point. Let me finish writing this there. So that's exactly true, actually. We can unconditionally show that catalytic log space is equal to randomized catalytic log space with a poly runtime bound.
so CL equals also.
No, okay, so this is again a subtle thing. So I have derandomization up here. What gives? The point is that the derandomization does not need to run in polynomial time. Yeah. So notice a consequence of this, and maybe a more evocative way of writing it, is that for randomized catalytic space, I can enforce a polytime run bound with no loss of generality. And if this were true for the deterministic world, then we'd be done. CL equals P, right? If polytime CL equals CL, then of course CL is in polynomial time. But
not equals contained.
it is contained in P, sorry, it's contained in P. I'm right. So this is kind of a weird thing that falls out when you just plug everything in. And I can say, by the way, that one of these directions just follows from, well, one of the directions, the way I originally wrote it, is just by derandomization. Of course, polytime bounded CBPL is contained in. I'm not using consistent terminology here. I should note one thing. There are a couple different papers, and the question of whether catalytic comes before or after things like non-determinism or randomization is completely up in the air. And I consider it a great strength of this paper that in derandomizing CL, we never have to ask this question again. Because it really bothers me. Which way to write it? Okay, I guess I'll be consistent. You can write it either way you want. I don't care.
I think that's totally wrong, and I'm getting angry about this particular.
Do you want me to switch it for both of them? I'm okay to do that. If it's any consolation, I prefer it the other way too.
So can I propose a plan for the rest of the seminar lecture?
Sure.
We would like to see through one in detail,
There are one in detail, yes.
right, but not through 2 or 3. So maybe, am I right? Oh,
So the reason, so I should note why these are in the same paper. The reason they're in the same paper is because this is a stepping stone. This is like the basic version of the technique that ends up seeing full expression.
Oh, then that doesn't make sense what I'm saying.
Correct. And this one is basically like an addendum. Again, one direction of it is just derandomization. The other one is like a slight tweak on this. So unfortunately I propose that we will be going through it. But if there's any consolation, it means you get them for free. Great. So in order to frame these results, I want to talk about I want to go back to this picture right here, and I want to talk about 2 inclusions that are not the ones that we necessarily care about, but that will kind of frame our discussion. The first is that BPL is contained in catalytic logspace. I was just trying that. It doesn't work. It's fine. It doesn't matter. The first containment we're going to look at is that BPL is contained in catalytic logspace. What's the time? I didn't want to use a box because the box is already used. And a circle is good.
Oh,
We have other colors. I don't know.
You're emphasizing.
Yeah, this is simply an emphasis. This is not a new class.
You're not scratching it away with some strange.
No.
strange way. It's an emphasis.
Yeah. No, we do not define diamond BPL in this paper. All right, well, I'm in too deep now, so there you go. The second result we're going to talk about is that catalytic logspace is contained in CD. Both of these results are going to sort of bring us to the main technique in this paper. And it's worth saying that beyond the actual statements here, in particular the first statement, which I think is a very, very impactful or like a flashy result, the real main contribution of the paper to me is the revival of a technique which kind of existed in the background of catalytic and hasn't seen a lot of use, even though it's a kind of nice, really pleasant result and a great introduction to the power of catalytic space. So this was a technique that was used to show this inclusion, but that ultimately didn't see much publication because it was subsumed by this TC1 result. Now it's kind of come back into the fray, and it's been used to solve, we're using it to solve a lot of different things. First here, and now recently we've come up with results in the non-deterministic world and the error-prone catalytic world using this here. So I personally am happiest about this paper because of the techniques. Yeah. But up until this, are there any questions about the setup statements as they're written, just catalytic as a whole? Great. Let's get to it. So, classical result 1. BPL is contained in CL.
I have a question about so we know examples of catalytic log space machines that take exponential time before they halt, right?
Correct.
And the exponential is like fully exponential in polynomial, or is it?
Yeah. So for example, you could I mean, we can artificially do this almost trivially. Take a catalytic log space machine and now extend the work tape by 1 bit. And what the work tape does is when that bit figures out whether you start in the all zeros catalytic tape. If it does, you flip a flag, then you count up until it reaches the all zeros catalytic tape again, flip that flag back and then do whatever you were gonna do before.
Cool.
Right? This thing takes truly exponential time on exactly one catalytic tape, and who knows what it does on the rest.
Right.
So yes, now this machine is stupid, but actually the machines that we're going to see in this talk, some of them do take exponential time, and for good reason. So that's going to be like, it's going to be important here. This is actually kind of the first time we are seeing catalytic algorithms that do something with exponential time. This TC1 inclusion, this catalytic logspace machine that contains TC1 always runs in polynomial time. In fact, like it kind of is oblivious to what your catalytic tape is. It just uses it as some generic mathematical object that like you never look at, you never analyze. It's using some arithmetic tricks and whatnot. On the flip side, the technique we're going to see here is so highly sensitive to the catalytic tape that you could see it as like the opposite of all the other techniques we use. Which is kind of nice. Okay, I was about to start drawing things out, but this one is comes from such a nice idea that we may as well just derive it from. What would you do if I told you you had access to this catalytic tape? Like, what would you try and do with it if I told you it had power? This is to the people who have never seen this before. Like yesterday.
I don't know, just use the catalytic tape as some sort of randomness.
Sure. Let's say we used it as a source of randomness. That would be nice. Use it to run your BPL machine. You have this big random string. Just do it. Now, what happens? Now, the all zeros tape is technically a random string. However, it may not give you the right answer. So, what would happen if this tape wasn't random? How would you deal with it? Or what would you do?
Using someone from common complexity in the cloud.
Yes. No, what would happen if the catalytic tape was the all zeros string? You look at this and you say, all right, well, this isn't going to be useful for randomness.
Maybe you can iterate over all possible configurations of the catalytic tape.
Ooh, good luck. You need to remember which one to reset to, though, is the tricky thing. So you have to know how many you've done, and this requires a counter, and this thing, you may not reach a random string too fast. So, but seriously, what happens if I just give you the all zeros catalytic tape? What would you do?
I could just run it on using that tape.
Yeah.
And then eventually I know it's all zeros, so when I'm done, I just reset it.
Reset, exactly. The all zeros tape, it's not a good source of randomness, but it's a really good source of space.
Yeah.
So that's not so hard. So can you extend that idea? What happens if I give you a catalytic tape that's not random?
Then we can compress it.
Very good. So this was the kind of the name of the technique as they gave it. People kind of, interestingly, when I talk to people about this, they kind of derive it from one of two directions. Either they're like, okay, you can use this as a source of randomness and then come up on compression later, or the exact opposite. The first thing they try to do is compress the tape. And then if you fail to do that, it's like, what do you have? Well, you have a random string, which is a pretty useful thing. That's, I guess, how you back into a result like this if I don't tell you that that's what we're going to prove. Nevertheless, let's just spell it out. So you have your input tape, you have your work tape, and you have your random string. Oh, you get this picture, you don't need to see it. All right, there are a couple of things that we need to satisfy in order for this to work. In particular, we need to be able to test for randomness. And second, we need to be able to compress. Now, it's worth noting that just having a random string, like one random string, may not be enough to actually get the right answer. You could have one or two random strings that are still bad for BPL. However, if you have a collection of random strings and you take a majority vote over them, as long as these strings are truly spread out enough, this you can prove will get the right answer. In particular, you can prove it for BPL specifically with the following test. I'm just gonna commit to it. If it's one of the other Nissan papers, then sorry. So let's take a collection of random strings, potential random strings R. And we're gonna be fixing fix a BPL machine. Capital M, computing a function f, and fix an input x. All right. So from here on out, there's a specific BPL machine M that we want to simulate to solve a specific function f, which is in the class BPL, and we're going to be doing it on a specific input x. So we're going to keep all those things fixed, and we're going to talk about the condition on the starting table. So we're going to define R sub sigma comma j as the set of random strings Ri, such that if you run your machine on input x and random string Ri for j steps, you get into the configuration sigma. So by configuration, I mean just the state of the BPL machine. What's written on the work tape, where the tape heads are, what the internal state of the machine is, all the information about the BPL machine. So this, I can define this for any of the polynomially many states sigma, and for any time step j. And time steps are polynomially bounded because it's known that BPL is contained in P, and in particular BPL machines can only run in polynomial time. That's probably worth saying. BPL in polytime. And it's for a reason that is also relevant to our discussion, which is that randomness in space-bounded computation is read once. This is an essential part of the definition of space-bounded complexity, is that both non-determinism and randomness are read once objects. And this avoids a lot of degenerate stuff. Turns out if you can reread your randomness or your non-determinism, suddenly you start to get into some kind of sketchy territory. One easy example of this is that if you can reread your non-determinism, NL equals NP, because you can just solve stat in the obvious way. Just guess an assignment and check that every clause is satisfied. Right? Yeah, it's just
In the randomness, it's less clear that there's a problem.
it is less clear that it is a problem. In fact, it takes some proving.
Can you do what is known? Is something known?
Well, okay, so if you allow randomness and you don't put a polytime runbound on it, then you get p space. So that requires kind of two conditions. Yeah, because you can just guess the transitions or just like flip until you get the right transition of your p space machine.
No, with polynomial amount of random.
Oh yeah, but if you put a polynomial runtime bound, I don't know what you get, but you know that it's still in BPP because BPP can reread its randomness, but you don't know that it's in P. We don't have BPL with randomization is in deterministic polynomial time. I don't know what else we get. I think, yeah, I don't know what else you get. Again, in the non-deterministic world, you just get NP almost immediately. So BPL is in polynomial time. We're in fact going to enforce the condition that it only has a polynomial amount of randomness. In other words, it has to halt with certainty. And yeah, read one. Okay, so those are just two small things that are worth knowing throughout this discussion. Anyway, because of that, this set that I've defined here is just parameterized by two log and bit objects. So, okay, there's polynomially many of these objects. I always forget this, some of the simplifying assumptions on BPL. The machine is going to run in polynomial time, which means we'll let it take a fresh random bit every time step. It doesn't have to use it, right? If it wants to make a deterministic time step, it can do so. But to make our lives easier, we're going to say it reads a random bit nevertheless. This, of course, doesn't change the behavior of the machine because reading one random bit is just as good as reading any other one. Okay, so we're gonna assume in particular that all of these strings have the same length, which is the runtime of the machine, which will say, we'll fix the largest runtime and just have it do nothing after it's solved the problem, if it does so on some instances. Okay, good. Now, for each B bit, 0 or 1, we're going to sort of split up this R sigma j into two sets based on whether the j plus first bit is 0 or 1. Now, from everything that I just said, the j plus first bit is, in other words, the bit that you're going to read immediately after the current time step, right? Since I'm forcing you to read a bit at every step in time, and this is exactly measuring the strings that reach this position sigma at step j. The j plus first bit, in other words, is going to be the one that is always read immediately after you've reached sigma on those strings. And now we finally reach Nissan's test. The test is simply that for every state sigma and time step j, the next bit is roughly balanced. By roughly balanced, I mean there's like these are within a 1 plus or minus 1 over poly fraction, where the poly depends on the size of these sets. It's actually not too hard to prove the fact that if it fulfills this condition, then the majority vote. Sorry, I should say, right, if the test fails or passes, then the majority over all Ri, when the bigger set R of the machine run on X with randomness Ri is equal to the correct answer. In other words, this collection of strings is random enough that you will get that the majority answer is correct. In fact, deterministically, it's not like correct with overwhelmingly high probability and whatnot. Essentially, you can say that the machine itself, the original machine succeeded probably 2/3, and if you fill this condition, then your collection of random strings is 2/3 minus some very small epsilon, like 1/100. It behaves like the original machine, plus or minus 1/100, and thus the majority vote is strictly greater than a half of the strings. And this is, this you can just prove kind of directly by looking at the configuration graph. Now, what does this mean for today? This means I'm going to think of my catalytic tape as my set R, right? My set capital R. So instead of thinking of it as one random string, I'm going to think of it as one. Why not? Bigger polynomial.
I mean, may I say a few words?
Yeah.
To see if I'm correct. So if you look at the configuration graph, right, you're in some configuration sigma at some point in time j. Now, if it was the original computation, what would be, now there's two options, right? You're going to toss a coin and either go to some configuration or some other. If it was the original computation, what would happen? Well, the coin is unbiased, so the probability of going left or right is going to be a half. Now, what this condition guarantees is that maybe it's no longer if you just sample instead of sampling a truly random sequence, right? You just sample a random string from your set.
Yeah.
What does the condition guarantee? It guarantees that once you reach state sigma at time j, the next bit, maybe it's not totally imbalanced, but it's imbalanced. It's a half plus times 1 plus or minus 1 over poly n, right? So this might create a little, choosing from this set of random strings might create a little distortion here on this. So this is not a real coin toss, but it's close enough to a coin toss that the behavior is going to be the same or close to it.
Right.
So in the end, this distorts the probability distribution on the final configurations just a little bit. 1/100 you sum up in total.
Yeah, that's a good way to put it. Essentially, if you just look at every time step, you know, the first time step, of course, you're exactly where you thought you would be. So you're just starting in the deterministic spot. Now move to the next step, right, there's this little epsilon bias of going left or right. And so you can look at the total bias of all the states, you know, it's, I don't know, like 2 epsilon or whatever. And then it turns out you can just kind of keep down this epsilon as you go out and out and out, and it will all work out as long as the state remains like a fixed quantity. But yeah, that's exactly right. It's just like you're starting at the beginning and you have slight biases at every step. At the end, you're not going to be that biased. Okay, good. So this tells us how we're going to operate. We're going to have our catalytic tape C, which we're going to think of as being the collection of random strings R. So we're going to chunk it up into a bunch of different random strings. And now we're just going to do this test. So this is enumerating over 2 order log n bit strings. I can just write those on my pure work tape, keep track of them, and run all of the tests. Just simulate the machine up to a certain point and see whether or not you actually reach where you're trying to get to. Notice it's always easy to reset the catalytic. Well, actually, we haven't even touched the catalytic tape really. We've been looking at it, but we haven't been writing to it. So there's no issue with regards to resetting yet. And if you pass sigma and j, if those tests both pass, then we're already guaranteed that we're done. You just run the machine on all of these random strings, and you take the majority mode. Right? You just keep a tally of how many zeros you've seen and how many ones you've seen. You write that down with log n bits, and that's it. And so what happens if this machine fails? If this test fails? So if it fails, it's going to fail for some sigma and j. So we're going to start by just writing those down on our free work tape. All right, we're running this test for sigma and j, and at some point we reach one which fails. And so we have that sigma and j written down for ourselves, and we're going to save it because this is going to be used in decompression.
So what's the square in the picture?
The square is the collection of all random strings. So the rows are the strings. Sorry. Yeah. So this is all.
So now I've written sigma and j.
Yeah.
In my work tape.
So let's take my free work tape.
I've written sigma and j.
Yeah.
And that means that out of the strings in R, I can actually just I actually know which of them are in R sigma j. And so you pretended that I just reordered them and put them.
Yeah, I moved them to the top. You're right. They don't necessarily have to appear at the top. However, once I've written down sigma and j, it's easy to identify which strings belong to R sigma j and which ones don't. I simply run the machine up to j steps and see if I end up in position sigma. So let's just think of this as being at the top without loss of generality, and make our lives a little bit easier. And what does the condition say? The condition says that if we look at the j plus first bit, so again, I'm writing the strings going along this way. This is highly unbalanced. This is a highly unbalanced string.
But actually, it's not highly imbalanced, right? It's close to a half. It's just not close.
Well, it's high. I consider it highly. Like a polynomial, a 1 plus or minus polynomial fraction.
1 plus or minus 1 over 1, right?
Right. If it's a small polynomial fraction and a big polynomial number of strings, in other words, if this set is like some huge polynomial size and the bias is like 1 plus or minus 1 over a smaller polynomial, that means that there's like a polynomial with number more zeros than ones, or ones than zeros. So this string is like really, really far away from being in the middle slice of the Boolean cube. In that particular one, actually.
But it's really not that wrong, right? It's a half plus.
Yeah, it's good enough. A polynomial is a very small fraction. This is kind of what it would look like. Yes. Anyway, so because I don't remember how it works, but it is possible to, if you have such a severe imbalance, you in fact need like what's your compression ratio? It's like quadratically imbalance. It's like if you have k K ones out of an n-bit string, you can compress it down to like, by a fraction of a squared over n, something like that.
Sorry, what, sorry.
K1 in an n string.
Yeah, if you have an n-bit string, which has, only K ones in it, or K zeros in it, but in other words, the smaller value. Then you can compress this thing to a fraction of its original size, which is like
This
this.
makes sense.
In other words, you compress it from n bits to like K squared bits, roughly speaking.
Great, but if K is larger than square root, then this is insane.
Yes, this particular algorithm won't say anything in this case. I'm sure there's a perfect compression, obviously, that does it, but there's like a really easy argument against this one.
No.
It's
You
not-
probably mean K beyond a half. Or something like this, right?
K beyond a half.
I mean,
Oh.
otherwise, because it's. again,
Oh, yes, yeah, no, sorry, yes, yeah, it's.
Oh, it's like n by 2 plus K.
N by 2 plus K. or
Yeah,
something.
maybe that's it, you're right.
So the number of ones is n by 2 plus K,
No, but then there's still something off.
plus K, and that should allow you to compress it, no, to
No.
something like K squared, I think, is that no?
No, but then K being small means it's not unbalanced. You should not.
Yes, right, that's it. Right, that's an issue. So it's. I have to pay. I'm not-
Actually,
I mean, it should be this counting of the, right? You
go
have-
to the h of it, K times n.
Yeah, it's maybe K root n or something, I mean, there will be some Chernoff bound that will tell you what the right fraction of all strings of length n is.
Right, so, okay, so then it's like a quadratic. Oh, the saving is quadratic, right? 1 minus K squared n?
Yeah, so it should be n by 2 plus K root n, the fraction of strings that have at least these many ones
Yes,
should be something like 2 to the minus K or some exponential with the
yes,
minus
exactly,
K, right?
that's what I would
So
expect.
then you save roughly K bits.
Okay, it's, so the compression rate is as follows. If you have n over 2 minus K bits,
Mhm.
then you can compress it into n minus K squared over n bits. Yeah, this is for the square.
Right, this is the Chernoff bound,
And
Did you
minus K squared by n.
right? So.
Yeah, this, right, Chernoff bound is telling
Yeah,
you what you should expect in terms of the compression. In terms of the actual algorithm, it's a cool in-place algorithm that actually does this compression for you.
Right, so
Without
these are,
important, yeah.
oh, the K squared.
Is that
So suppose K is something like S root n. Right,
S
then you
root
just
n.
get S squared, n minus S squared, oh,
N minus S squared, yeah.
Yeah,
I didn't even realize the square, oh, because the Chernoff has the square.
Yeah.
Yes, so
Good,
good, yeah. Right, yeah, that makes sense, that's the Chernoff.
yeah,
Okay, and you can compress it in place.
and you can compress it in place, yes, that is the part that,
Right,
I always forget how this algorithm works, but essentially,
it's not obvious.
yeah, it's not obvious, it's some combinatorial, it uses like, yeah, some combinatorial properties, it's quite cute.
It's in Nissan's paper?
No, so
Is there-
Nissan's paper
okay.
actually gave this condition in order to say that there's like an efficient way to test for random strings as to whether or not they're good enough for BPL. So it was the next step, and this is an internal write-up that I think made it into like maybe Yuvka's master's thesis, except I can't find it.
Yeah, so this, so this compression thing in place, is in this unpublished write-up.
Right. It basically never solved like that.
Yeah, and it's not so obvious how to, right? So the claim is that the number of strings is 2 to the n minus K
Yeah,
squared by n,
exactly.
right? But how do you go from, you have a string which is in this small family, how do you actually compress it so that you free up some memory, you want to compress, and you have to do it,
With a
you don't have
decompression.
extra space, right? To do it, you have to do it in the position where these bits are. And it's not super obvious how to do it, but you can do it. And
Okay.
decompress then after, which again is not obvious.
Yes, no, it's quite nice, and At one point I knew it well, now I don't. But it is great that it works. And in particular, like taking message is that once you've reached this point in the algorithm, you're on a string that is in such a small set of all possible strings of length, again, polynomial, that compression should presumably be possible. Like this set is easy to identify, you know exactly where it's written on the catalytic tape, because you can always test whether or not you're in this set. You've written down this stuff, so you know it's in the J plus first position. You're kind of perfectly primed that once you have this clever compression algorithm, you can force everything into a small enough space, at which point you're left with a bunch of zeros at the beginning, and this you should think of as like poly n in length.
Where n is not the length of the R, right? So n is.
No.
N
So
is
you have to
the-
make everything, you have to make everything large enough that the amount of space you free up when the dust settles is enough to brute force your BPL machine. You know, it's enough to run the polytime algorithm which contains your BPL machine. So that is, you have to play with the parameters and get it, and you end up with an extremely lossy algorithm in terms of catalytic space, but who cares? That's the end of the game. Oh, yeah, really cute algorithm. Unfortunately, of course, this relies on the fact that we have this extremely efficient test for good randomness for BPL, right? BPL is not a very expressive class. You can fool it with this like really stupid test, essentially. Like any collection of strings, no matter how easy, that fulfills this test is good enough to get the majority vote answer for BPL. And when we move to derandomizing something like CBPL or whatnot, we don't have these kinds of tests anymore. At least they're not obvious. Which means if we're going to try and use this style of approach, we need to be thinking in more clever ways.
So with CBPL, the main problem is that the state is too large.
Yeah, so, right, I haven't even gotten around to defining CBPL, but intuitively, it's like, all right, now I finally just draw a picture. So your BPL machine had an input tape, a work tape, and a random tape. And your catalytic tape had an input tape, a work tape, and a long catalytic tape. Now, if you have a CBPL algorithm, what happens? You add a catalytic tape here, and well, I'm just extended by that many bits to simulate it deterministically. So it's not like actually simulating the workings of the algorithm seemed that hard if I had a way to de-randomize everything. But like trying to do these kinds of tests when we can't even write down one state's intermediate state sigma of, of the tape is completely,
That's the problem.
no chance. But even if you could do that kind of thing, this test may not be enough to get it. You know, I can store one intermediate state. I mean, looping over all these is, yeah, going to take exponential time. So that's,
Right, that bit.
yes, okay. Yes,
Oh, I see.
yeah, I mean, some of these states are even unreachable. Yeah, you gotta be a little bit careful about resetting it. Yeah, great proof. If you get a chance to read a Nissan paper from the early 90s, do it. It's like, they're all extremely insightful. All right. Let's move forward to the second diamond. Start defining this. Do this one, and then I don't know, do people usually take breaks at the hour mark?
Yeah, you should take a break.
Sure, good. Then after the CPP proof, I think would be a perfect time. So. CL is contained in CPP. To prove this, let's first go to an argument that pretty much everyone, I would assume everyone here knows. L is contained in P. And if you didn't know that, then I'm sorry for delaying it this long, because that's kind of an important point. Logspace is in polynomial time. And the reason why is because your configuration graph of your logspace machine can only have polynomial size. Right? We're assuming that I'm thinking of the configuration graph as having everything that you that's a deterministic machine. As having everything that you need to run the machine at a given time step. which means in particular, if you ever repeat a configuration in the way that I'm thinking about it, you've essentially entered an infinite loop because there's no information that will allow you to break out of this. If the work tape is the same, the tape head is the same, the state of the machine is the same, then it is the same situation. And of course, again, your workspace has size S, an S-bit work tape, which is logarithmic, translates to a configuration graph of size 2 to the S. Thus, every logspace machine holds in polynomial time, and that's the whole proof, right? Of course, the polynomial time machine can actually write to a logarithmic number of working cells. That's a single machine. Now, that isn't the case for catalytic logspace, right? This is a kind of lengthy diversion into something that seems completely unrelated because a catalytic machine has, a work tape of size S, let's say, and a catalytic tape of size C, which are log and poly respectively. Which means you have 2 to the S times 2 to the C in phase. And of course, for C being polynomial, this is still polynomial. And so now we come to a question that sort of popped up earlier. Can you just always be running an exponential time? No matter what your starting tape is, you do something that will take you exponential time. And the saving grace is that the answer to that question is no. So let's think about some start state tau. So this was like a start state. Throughout this talk, we're going to think of start state as being defined by when the working tape is all zeros, right? Again, think of the working tape as holding all the information like pointer heads, state of the machine, etc. So when it's all zeros, that's going to be our sign that things are just getting started. So at the beginning of some computation path, that's exactly what we have. We have some state of the catalytic machine, let's call it tau. Throughout this talk, tau is going to be the state of the catalytic tape. And we have the all zeros string in the working number. And now we have our transitions sort of the same way as it was before. And eventually, we of course reach a configuration with the correct answer. In particular, it's got tau written on the catalytic tape again, and it's got the answer. Great. Now, as we said, this thing can be exponentially long because there are exponential number of configurations in the graph. The question is, what happens if I look at 2 of them? The tau from 0 is another start state, let's say, and it also follows some long configuration graph. And the question is, can this ever happen? Can it ever be the case that tau prime and tau share configurations along their configuration path? Remember, I'm thinking for a fixed input x. And I think that the answer to this is no. For the simple reason that the machine has to reset, right? Once we've reached this state, we have lost any information about where we started, right? The only thing that actually tells us, quote unquote, where we started is the promise that at the end of it, we will reach a final configuration where the starting catalytic tape is written. However, if 2 of these merge in, and you only reach one end state, then the game is over because you can only reset to one of these 2 and not both. So what does that tell you? That tells you that actually the configuration graph, like a deterministic logspace machine, is one line, plus maybe some disconnected islands that don't do anything. Here, putting aside those islands and whatnot, we have a collection of lines, a disconnected collection of lines. And thus, the total number of configurations being 2 to the S times 2 to the C is fine because we have at least 2 to the C connected components, right? One for each possible starting catalytic tape. Which means the average size, or let's say length of a computation is 2 to the S, is at most 2 to the S minus 2 to the C divided by 2 to the C, the total number of starting positions, which is once again just 2 to the S, which is polynomial. And thus our ZPP algorithm is very simple. Pick a random starting catalytic tape and run it. That's the whole thing. So with probability way greater than 2/3, and you can just analyze this, with probability way greater than 2/3, the computation will take at most like 2 to the 2s time. And furthermore, your CL machine will never get the wrong answer, no matter which catalytic tape you start with. Which means the worst that can happen is you pick a bad catalytic tape and it takes longer than this amount of time. And so once you've gone for 2 to the 2s steps, you can safely say, I don't know what the right answer is. So this is a 0 error procedure. Again, if you think of it in the like BPP world, it's as I described, think of it as NP. In NP, you can just guess a good starting catalytic tape and then run the machine forward for 2 to the S steps.
Right.
Yeah. Right. So these are going to be two of the two kind of essential pieces of our proof. The first is this idea of compressor random, wherein we want some kind of nice condition on our catalytic tape, a random condition, which we can detect. And if we pass that, if we succeed at that condition, then our catalytic tape will already be in the right position to be used as it is. Whereas if it's in the wrong configuration, we're going to come up with a compression technique wherein we can brute force.
Okay.
The second is this idea of the bounded runtime in expectation. The fact that if we start a random starting tape, we will end up with a short configuration graph.
So the reason it's not in ZPL is that,
Oh, you can't
You can-
connect the actual operation of the machine, right?
sorry,
ZPL, like,
I mean, yeah,
well, how do you
you can't.
don't even have a catalytic tape, like you don't have a poly length to work with, even catalytically, right?
You have poly randomness, but the only problem is you can't read it multiple times. That's
You can't read it multiple times, and also in no world are we allowed to write to our random tape, I guess, is another thing.
oh, right. All right, sure.
Yeah, right. No problem. Yeah, again, these are all issues that are completely moot when it comes to P. You can always just start by writing down your random tape on your working memory, and then you can kind of do whatever you want with it. All these issues are much more sensitive when it comes to space-time complexity. Excellent. So yeah, let's take 5, 6, 7. Okay. Boy. I don't see the lights flashing. No, it's fine. Okay. All right. When last we left our heroes, we had two big ideas. Idea one. If the catalytic tape is not random. And as Sale pointed out in the break, random means random with respect to something you want to do, like random against CBPL, pseudo-random against CBPL. In other words, but it doesn't have this kind of random property, compressor. Idea two is that a random starting catalytic tape implies that your machine runs for all time. Right? So now that I've written these two ideas next to each other, it might kind of imply or suggest a natural consequence of these two together, which starts to put us onto our main path for today. So let's just say idea 3. Either running all the time or compressed. So that's kind of the starting idea for everything that we're going to see today. It's that one nice condition that we get out of randomness is that we are in a good region of the initial catalytic, a good initial configuration for the catalytic tape. And remember, the name of the game today is derandomization and also poly runtime balance. So this is going to be a really nice point to start. Now, we're going to have to define a way to actually detect this condition. And we're going to have to find a nice way to compress. And one of those two is really easy. It's not hard to detect whether or not a catalytic tape is going to take too long, because you just run it for the correct amount of time and figure out if it's still running. The compression is going to be where things get interesting, not difficult, but interesting. And it's going to kind of lead us to the rest of what we want to do. So, because I want to chase down these ideas, I guess I'm going to start by doing the theorem that no one wants to hear, which is theorem 2, the polynomial time map. Because actually, this gets us about 90% of the way there. These observations as we've seen them. And I want to do that before we really jump into the derandomization stuff, which will take the bulk of our time afterwards. But I'm going to try and cheat my way around. So yeah, so let's just start and see what happens. So we have our BPL or our CL machine MCL, and we have some input X. And we can just run it forward for, let's say, steps. And of course, think of I as like some reasonably large polynomial, something where if I start with a random catalytic tape, starting tape, then I should be done. Actually, let's just put this as the initial configuration. It's now, and again, the all zeros state is going to be my indication. Well, my all zeros work tape is an indication that I'm at the start in a starting configuration. So I'm going to run this machine MCL X. Let's just say it's a CL machine. I run forward for I steps, and one of two things happens. Either halts with F-dots. Right? Or second, it's in some intermediate configuration. It's called tau I. This is the state of the machine after I steps. And the question is, how do we compress knowing that this thing has taken this long? Well, let's extend our catalytic tape by a little bit. So I had tau written here, it's just the alt zeros initially, and I transformed it into tau I vi. Well, where did I come from? I said if it's a large enough polynomial, then almost all the tapes should die out beforehand, and only a few of them survive. And the cute trick is to get I from your catalytic tape. So let's extend the catalytic. We're simulating this MCL machine by a bigger CL machine. So let's actually pretend that the number I is written on the catalytic tape. And of course, since we're not touching that part of it, at the end of it, we're just going to see exactly this. And here's the idea. How big does I need to be in order for this, in order to expect that this won't happen? Well, the average runtime is like 2ps steps, where S is the length of the free word tape. So if I has a few more bits than that, like S plus 3 bits or something like that, then a random catalytic tape won't take that long. But furthermore, I claim that given just these two pieces of information, I can actually recover this state.
You can recover the i's.
The original state, which is tau, of course, the all zeros is easy. But in particular, I can recover both tau and I. And the reason is that space is reversible. It is reversible. So this is a classical theorem from 2000. When I say it's classical, it's from 2000. It's a younger crowd. It's fine. So this is by Lange, McKenzie, and Tapp. And it says essentially that if you have a space S machine, you can increase the space by like plus order 1 many bits. So like really just a constant number of extra bits of working memory, such that you now actually have 2 machines, we can call them M forward and M reverse, and M backwards. Where this is what M forward looks like, and M reverse looks like the opposite.
This is in the configuration graph.
This is in the configuration graph. So in other words, it doesn't act exactly the way that your original machine M did, but its configuration graph has almost the same size. You know, you've only blown it up by a constant factor by adding order 1 many bits to the work tape. And now, of course, it solves the same function. And anytime you could take a step forward, you can also take a step back. You can kind of walk back to where you were immediately before. There's a nice proof of this. Basically, it involves taking like an Eulerian tour around the configuration graph. And so the important thing is like in the configuration graph, the way I've written before, it looked like a line, right? But there are actually potentially dummy states hanging off the edge. So when you try and reverse, you might end up somewhere that you weren't supposed to be. And so an Eulerian tour comes in by just basically saying like, go around these islands. While you can have these hangers off, since everything has out degree 1, you'll never get caught in an infinite loop or kind of find yourself in the wrong place. So this is not too much of an issue. And the only thing you need to write down essentially is like, you know, now it's a little bit finicky, but basically you say, am I before the transition or after the transition? So that you can know which transition you just came from, so you can rotate kind of to the next lexicon, the next transition in order. It's just some like little nonsense, but the takeaway from it is that you can assume deterministic space-bounded machines are reversible. And that holds for catalytic space as well. This was written in, again, Yufka Deluxe master's thesis, write-up, etc. And we kind of go through some pains in this paper to just spell it all out again and get the details nailed down. So if you're interested, we have a kind of full write-up in the appendix of our paper about how to get this to work. But it's a very similar Eulerian tour argument. In fact, it's essentially the same. And a crucial point here is that, again, you might have 2 catalytic configurations. And there might be some kind of like, you call it like a bridge state, where depending on what X is, you know, if Xi is 1, it goes this way, and X0 is, if Xi is 0, it goes this way. But I'm thinking about this being reversible once you've fixed an input X. Once you fix an input X, it's a deterministic machine, everything is at degree 1, so one of these 2 edges won't exist. So there's no issue that when you run this, you're going to end up in someone else's configuration, some other starting tab. So don't worry about that. And the takeaway of this is that if we convert the machine to this form, our catalytic machine MCL, or again, just assume that it was in this form to begin with, then this forward and backward behavior holds. And in particular, it takes the same number of steps to go forward. You know, if you go forward I steps and then go backwards I steps, you end up at the same place. In particular, if I start here and I start running backwards, I'm only ever going to reach 1 starting configuration of the CL machine. Again, we can recognize the starting configuration as being all zeros in the workday. You'll only ever reach 1, which means it was the one you started with. And the number of steps it will take to actually get there is precisely I. Which means, given this state, I can simply start a counter on my on some additional space in my logspace work tape, run backwards until I hit the state of this form, and then return whatever the value of the counter is and whatever the catalytic tape says at that point. Right.
So the VI and tau I, if I have tau I on the tape and I have VI,
Right.
then by running backwards, I can obtain I.
Correct.
But now you've saved some bits because actually VI is a lot smaller than I.
Precisely. So I erase I here because once you've reached this intermediate state, the next thing you're going to do is erase I and copy VI here. And then of course free this up. And the point is that by definition, we picked I to have a longer number of bits than VI.
Oh. Oh, maybe.
Catch the